Okay, folks, so in this section we get the fundamental theorem of calculus. And one way to look at what the fundamental theorem of calculus does is it relates these two seemingly unrelated topics: computing definite integrals, computing the area underneath the curve, and finding derivatives, and finding instantaneous rate of change. They seem like they might be unrelated topics. Okay? And the fundamental theorem is what connects them together. All right? So the first thing I want to do, is define what I'm going to call the area function. Okay? So I'm going to call this thing right here the area function. The area function. Okay? That's my own terminology for it, but it seems to fit. Okay? So I want you to pause for a minute and think about what this function's doing. So I'm talking about g of x. I would like everyone to read over that and take a minute to think about it. So, sorry folks, I forgot to. So identify what your independent variable is, and then see where it shows up in the expression. It shows up as the upper limit of integration. Okay. So we've got sort of two functions that we're considering here. Okay. We've got the function g of x, this area function that I want to talk about, and then we've got an underlying function. So let's look at the picture of this. So we've got some underlying function, f of x. Normally I would label it as f of x, but what's the issue? I'm going to have another x that's really my independent variable, right? So instead of labeling it as f of x, I'm going to introduce a new variable here, a dummy variable. Sorry, t, that's what we call you. Okay. So we'll call it f of t. Okay. And this is along the t-axis here. This is the t-axis. Okay. So then what do? Well, we take our two limits of integration. Here's a for our lower limit. Oh, what is our upper limit of integration? It is the variable. It is the variable. So this has a variable upper limit of integration. Okay? So here would be x. And so then what would g of x be? G of x is this number. G of x is what you get when you compute the area underneath the curve. So do you see why I'm calling it the area function? Okay. Now, I'm sorry, I'm sort of, I'm still stuck in the 20th century. I can't pick up this x and move it along and show you how this green region grows. I wish I could. I wish I could pick up this x and move it over to here and then show you how this region had grown as I slid x to the right. Or if I slid x to the left, or even took it past a, I could move this x around. That is the variable. Does everyone understand what I'm saying here? So if I had a way of sliding this x back and forth, you would see that the value of g of x would change. In fact, let me just ask you, what would g of a be? What would g of a be? Yeah, it would be the integral from a to what? A of f of t dt. And so you would see that, right? If I slid this all the way back to where a is, I'm asking for the area of just a point underneath the curve. So that would be 0. And you can see if this is a positive function, if f is a positive valued function, the further I move x to the right, the greater the value of g of x is, right? Okay? So spend some time thinking about this function. We do design questions based upon your understanding of this function. Okay? So spend some time thinking about it.